Hey guys, in this video we will be going over how to simplify expressions containing higher roots. So let's extend what we've learned about simplifying square roots to higher roots. The product rule for square roots will be similar to the product rule for higher roots. So if the nth root of a and the nth root of b are real numbers, then the nth root of a times the nth root of b equals the nth root of a times b. And we can use this rule in either direction. Also, the indices of the radicals must be the same in order for this rule to apply. So for example, if we have the cube root of 2 times the cube root of 7, we can use the product rule for higher roots and simplify this to cube root of 14. So this rule is going to be useful for simplifying higher root radicals of any index. So let's write down the conditions for when a radical is simplified. So if we let p be an expression and n be an integer greater than 1, then the nth root of p is completely simplified when all of the following conditions are met. The first condition being that the radicand does not contain any factors other than 1 that are perfect nth powers. The second condition is that the radical does not contain variables with exponents greater than or equal to the index of the radical. The third condition is that the radicand does not contain any fractions, and the fourth condition being that there are no radicals in the denominator of a fraction. So let's do some examples. To simplify this radical, we need to make sure that the radicand contains no factors that are perfect cubes other than 1. And some perfect cubes include the following. So 250 actually contains a factor of 125 that's a perfect cube. Therefore, this can be simplified. So we can rewrite the radicand as 125 times 2, and then using the product rule for radicals, we have the cube root of 125 times the cube root of 2. And the cube root of 125 is 5, and we can't simplify the cube root of 2 any further since the radicand does not contain any factors that are perfect cubes besides 1. Therefore, the cube root of 250 simplifies to 5 times the cube root of 2. For the next example, to simplify this, we need to make sure that the radicand contains no factors that are perfect fourth powers. And some perfect fourth powers include the following. So 48 actually contains a factor of 16 that is a perfect fourth power. Therefore, this can be simplified. So we can rewrite the radicand as 16 times 3, and then using the product rule for radicals, we have the fourth root of 16 times the fourth root of 3. The fourth root of 16 is 2, and we can't simplify the fourth root of 3 any further since the radicand does not contain any factors that are perfect fourth powers besides 1. Therefore, the fourth root of 48 simplifies to 2 times the fourth root of 3. Now let's go over the quotient rule for higher roots. This will also be similar to the quotient rule for square roots. So if the nth root of a and the nth root of b are real numbers, then the nth root of a over b is the same as the nth root of a over the nth root of b, where b is not equal to 0. And again, you can use this in either direction, and you can only apply this rule when the indices are the same. So let's try a few examples. For this example, in order to be simplified, we can't have a fraction in the radicand. However, we can actually simplify this fraction first. This fraction simplifies to negative 27. And now we can take the cube root of negative 27, which is negative 3. For the next example, we can approach this in one of two ways. The first way would be to use the quotient rule to write this as one radical, and then simplify the fraction. This will give us the cube root of 48, and this radical can be simplified further because 48 contains a perfect cube of 8 as a factor. So we can rewrite this as the cube root of 8 times 6, And using the product rule, we have the cube root of 8 times the cube root of 6. We can simplify the cube root of 8 as 2, and since 6 contains no perfect cube factors other than 1, this radical is already simplified. So our expression simplifies to 2 times the cube root of 6. The second way to approach this would be to simplify the cube root of 96 first. So 96 contains a perfect cube of 8 as a factor, so we can rewrite this as the cube root of 8 times 12, and use the product rule to simplify. So the cube root of 8 times the cube root of 12 over the cube root of 2. We can simplify the cube root of 8 as 2, and since 12 has no perfect cube factors, we rewrite it as is. So this is still not simplified because we have a radical in the denominator, but what we can do is use the quotient rule to rewrite this as one radical, and then now we can simplify the radicand. So we get 2 times the cube root of 6. Now let's go over how to simplify radicals containing variables. So recall that to simplify square roots containing variables, we just divide the exponent of the variable by 2, which is the index. So for example, the square root of x to the 6th power can be rewritten as x to the 6 over 2, which simplifies to x cubed. If the exponent is not divisible by the index, we can write it so one of its factor is. So for example, the square root of x to the 7th has an odd exponent, so we can rewrite x to the 7th as x to the 6th times x, and then using our product rule, we can simplify. This gives us x cubed times the square root of x. We can use the same approach for higher roots. So the cube root of x to the 3rd power is x, since x raised to the 3rd power is x cubed. We also know that we can rewrite this as x to the 3 over 3, which reduces to x to the 1st power, or simply x. And if we have the cube root of x to the 6th power, this will equal x squared, since x squared raised to the 3rd power equals x to the 6th. And again, we can also rewrite this as x raised to the 6 over 3, which also reduces to x squared. And for the 5th root of x to the 10th power, the exponent on the variable is divisible by the index, so we can rewrite this as x to the 10th over 5, which reduces to x squared. Okay, let's try a few more examples. We want to simplify the following radical completely. Since the exponent on the variable is divisible by 3, we can rewrite this as x raised to the 15 over 3, reduce the exponent, and this simplifies to x to the 5th power. For the next example, notice that 16 is a perfect 4th power, and the exponents on the variables are divisible by 4, so we can use our product rule and simplify. So the 4th root of 16 is 2, and the 4th root of x to the 24 can be written as x raised to the 24 over 4, which reduces to x to the 6th power, and the 4th root of y to the 8th power can be rewritten as y to the 8 over 4, which reduces to y squared. Therefore, this simplifies to 2x to the 6 y squared. For the next example, we can use our quotient rule to write these as 2 separate radicals. And notice that the exponent on the variables are divisible by the index. So we can rewrite this as x raised to the 10 over 5, which reduces to x squared, over y raised to the 30 over 5, which reduces to y to the 6th. And now our expression is simplified. So if the exponent of the variable is not divisible by the index, then see if we can rewrite it as factors so that one of those factors' exponent is divisible by that index. So for example, the 4th root of x raised to the 23rd power, notice that the exponent 23 is not divisible by the index 4. So we can rewrite x to the 23 as x to the 20 times x to the 3, so that the exponent on one of those factors is divisible by 4. So now we can use our product rule and simplify. The fourth root of x to the 20 can be rewritten as x raised to the 20 over 4, which reduces to x to the 5th. And the fourth root of x cubed is already simplified. Therefore, our expression simplifies to x to the 5th times the fourth root of x cubed. For the next example, we can rewrite 56 as 8 times 7, so that one of its factors is a perfect cube. For x raised to the 16, since the exponent is not divisible by the index, we will have to rewrite it so that it is. So we can rewrite this as x to the 15th times x, and now we have an exponent that's divisible by 3. We'll have to do the same thing for y raised to the 8th power, since the exponent is not divisible by 3, so we can rewrite it as y raised to the 6th power times y squared. And now we can use our product rule and simplify. So the cube root of 8 is 2. Cube root of 7 is already simplified. Cube root of x to the 15 can be rewritten as x raised to the 15 over 3, which reduces to x to the 5th power. Cube root of x is already simplified. And the cube root of y to the 6th power can be rewritten as y raised to the 6 over 3, which reduces to y squared. And then the cube root of y squared is already simplified. And we can rewrite this so that our non-radicals are written first, and then using the product rule, we can write the radicals as 1. Therefore, our expression simplifies to 2x to the 5th y squared times the cube root of 7xy squared. And the last topic that we need to go over is how to simplify radicals if they have different indices. So for this example, we want to simplify the radicals completely. And notice that they have different indices. We won't be able to use our product rule on this. So what we can do is we'll have to rewrite these radicals to rational exponent form, and then see if we can simplify. So we can rewrite this as x raised to the 2/3 times x raised to the 1/2. And since we have the same base, we can use the product rule for exponents and add the exponents. So to add 2/3 plus 1/2, we need to find the least common denominator, which is 6. So we can multiply the first fraction by 2 over 2, and the second fraction by 3 over 3. And now we can add 4/6 plus 3/6, which is 7 over 6. And since we want to write our answer in simplest radical form, we can convert this back to a radical as the 6th root of x raised to the 7th power.